We need lists of measurements, whether it be for population, prices, debt, pollution. We're always taking measurements and we're putting them in a list. And normally this list has an order to it. It may be year over year population. And that's what a sequence is. We just put mathematics behind this list.
From the first perspective, a sequence is an infinite ordered list of numbers. For example, we could have 1 followed by a half, followed by a third, followed by a quarter, etc. Keep going, 1 over n plus 1. So this first one, we would label it as A1 and we refer to it as the first term. Similarly, the second one, which is a half in this list, we'd call A2 and we'd refer to it as the second term. The nth one, 1 over n, we'd label that as an and refer to that as the nth term. How about an example of another sequence that starts 4, 6, 8, 10, 12? What comes next?
14.
That's a great normal answer. However, mathematically speaking, it could have been anything. There's not enough information since there's no rule for generating the next sequence numbers. In fact, it is pi followed by e followed by different numbers. Until we have a definition of how to come up with these terms, we just don't know. To motivate the second perspective, we will plot this sequence. So in particular, after labeling the vertical axes as A and the horizontal as N, we take 4, which is A1, the first term, that would be plotted at the point 1 and A1, i.e. 1 and 4. The second term, which is 6, would be plotted at 2 and A2, which again is 6. And we go on and we plot all of these 7 points, the last two being 6 pi and 7e. It appears that we have graphed some form of function, with n being the independent variable and a being the dependent one. So for example, the value at 3 is 8, which is a3. The value at n would then be an. This function would only be defined on the natural numbers, i.e. the positive integers. So for this second perspective then, we can consider a sequence, a mapping A, from the natural numbers into the real line. We use a sub n, enclosed in braces, with an optional lower script n equals 1 and superscript infinity to denote the whole sequence instead of just the nth term. Our first important class of properties is those of monotonicity. For example, in census data, is the population of a city heading up or is it heading down? Increasing means that an is less than an plus 1 for all n. So in other words, if we go right, we go up. Similar to that, but allowing the ability for a sequence to just stay flat for some of the time or the entire sequence, we have the property of non-decreasing. Non-decreasing means that an is less than or equal to an plus 1. So if we go right, we do not go down, which is subtly different than increasing. So increasing doesn't mean non-decreasing. Sometimes people say strictly increasing. However, we will not do that. Non-increasing then means that an is greater than or equal to an plus 1. If we go right, we do not go up. And finally, decreasing means an is greater than an plus 1. If we go right, we go down. The other important class of properties is boundedness. Bounded above means that the sequence never exceeds some positive level c, while bounded below means it never dips below some value minus c. And finally, bounded means that neither occurs. In other words, every term is bounded in magnitude by some positive number c. At the beginning, we asked what was the next term in a sequence, and a logical but incorrect answer was given. And the reason why this answer was not the right answer was because we gave no formula to specify the term. Any number was possible. Like for a regular function, we often give a formula which shows us how to define the dependent variable in terms of the independent one. So for example, we have the function f of x is equal to 1 over x. For a sequence, we'd have a similar definition, a of n is equal to 1 over n. We could have a function, f of x is equal to sine x, but we could also have a similar sequence, a of n is equal to sine n. That is, the dependent variable is the function sign of the independent. Now more can be done for a sequence. Here's a cool example. The function f of x is equal to minus 1 to the x does not exist because minus 1/2, minus 3/4, etc. These do not exist as real numbers. But because of the discreteness of the domain, the sequence an is equal to minus 1 to the n, which means minus 1, 1, minus 1, 1, does exist. With the term formula, we can precisely specify a sequence and answer interesting properties about it. For example, what about the sequence an is equal to the square root of n plus 1 minus the square root of n? Well, that's a function of n. And we could pose the question, is this sequence decreasing? Also, is it bounded below? Well, we can calculate the various terms in the sequence. So by plugging 1 in, we find that an is equal to the square root of 2 minus the square root of 1, which is 1. So we have 1.41 minus 1, which is 0.41. Then we could plug 2 into the term formula to find the square root of 3 minus the square root of 2, and that's approximately 0.32. And then the next one, the square root of 4 minus the square root of 3 is approximately 0.27. Square root of 5 minus the square root of 4 is approximately 0.24. And then 0.21, 0.2, 0.18. And what we could then do is plot these with the a being the dependent variable on the y-axis and n being the independent variable. And plotting these points, what we could certainly observe is that does appear to be decreasing, and that would be true. And then to consider the bounded from below, is there a horizontal line that it does not dip below? And that also appears to be true, and indeed it is. Next, we can move on to another example, which is a little bit more complicated, just because it has compositions of the same function repeated. So the term formula here is an is the natural log of the natural log of the natural log of the natural log of 20 plus n. And we could ask, well, is this increasing? Is this bounded above? And once again, we could do the same thing. So we could take the 4 times iterated log of 21, so that's n is 1 plus 20, and then take those subsequent logs, and we'd come up with an answer of minus 2.23 just by plugging them into our calculator. And then if we repeated the process with n is 2, so we started with 22 and then took those iterated logarithms, we'd come up with a number of minus 2.11, and then negative 201, then negative 1.93, then negative 1.86, then negative 1.79, then negative 1.74. So here what we've done is we've just jumped from 7 all the way to 100, because what we really want to do is have a feeling whether this is bounded above or not. So for 100 it's negative 0.8, and then indeed for 1000 it's negative 0.42. So we plot these first 7, and it seems that it's increasing, and indeed this is an increasing sequence. And the increasing nature of this would just follow by the fact that the logarithm is an increasing function, and compositions of increasing functions are increasing. So this plot coincides with our intuition. It also looks like it's bounded, say by 0 or some positive number drawn here as c, but in actual fact this is unbounded. This is an unbounded sequence. And so this is an indication that plugging things into a calculator does not always lead you to the right conclusion. There are some common sequence types to keep in mind. For example, arithmetic sequence is one that starts with a number and then adds a constant shift. So for example, we could define an, the nth term, as 2 plus 3 over n. That constant shift would be 3 over 2. It doesn't have to be positive. It doesn't even have to be rational. Anyways, in this example, the first 4 terms would then be 7 over 2, i.e. 2 plus 3 over 2, and then 5, i.e. 2 plus 2 times 3 over 2, and then 13 over 2, and then 8, etc. An even more popular sequence is that of a geometric sequence, and that is one that starts at a number and then the next term is a constant multiplier times the previous one. So in this example we have a1, that's 3, that's where it starts, and then we multiply it by a half, and then another half, etc. as we move through the terms. So the first 4 terms then would be 3, and then 3 times 1 half, and then 3 times 1 half squared, which is 3/4, and then 3/8, etc. Another general type of sequence that's also very important is an alternating one. So that's just one where the signs change back and forth. An example here is -1 to the n plus 1n. So the first term would be -1 to the 1 plus 1 times 1, so that just gives you 1. And then you'd move on and you'd have -1 to the 3, which is -1 times 2, so you get -2, and then you get 3, and then -4, etc. We can also define terms in a sequence recursively. So in particular, we could have a first order recursive equation where the nth plus 1 term, an plus 1, is defined as a function, not of n, but rather of the previous term, an. For this to make sense, we have to have one initial value, a1, to start the recursion. A second order recursion would have the form an plus 1 is a function f of an and an minus 1. And in this case, because you're looking at the 2 previous terms, to start this one up, you'd have to have a1 and a2 given. Let's take an example. As a first order example, let's say a1 is 0 and an plus 1 is the square root of 1 plus an. So you're always taking the previous one, adding 1, and then taking the square root. And in our calculator, we would find a1 is 0, a2 is 1, a3 is 1.41 or root 2, and then we'd find a4 is approximately 1.55, 1.6, 1.61, 1.62. Comparing to our general first order recursive equation formula, we would have f of an is equal to the square root of 1 plus an. As an example of a second order recursive equation for a sequence, we use the famous Fibonacci sequence. Here a1 and a2 are both 1, and then the next term is defined as the sum of the 2 previous ones. So an plus 1 is an plus an minus 1. Then we can compute these values successively, so we have 1, 1, then 1 plus 1, which is 2, and then 1 plus 2, which is 3, etc. to get these terms. And then comparing this to our general formula for the second order recursive equation, we find that f of an minus 1, is just equal to an plus an minus 1. So for take-home messages, we can think of a sequence as an ordered list of elements, or else we can also think of it as a function. And to be able to analyze this sequence, we have to give the term some form. So we either make an a function of n, or else an a function of previous terms. A couple of important properties for sequences is monotonicity. Is it increasing or non-decreasing? And boundedness, from above, below. And these properties are a little subtle for your calculator. And then we have the important common sequence types, such as the arithmetic, geometric, and alternating sequences.